Hello everyone. Today we will discuss about chemical potential. I will try to develop a basic concept about this chemical potential, and this topic is very important for the graduate and postgraduate students in terms of competitive examinations like NET, GATE, JAM. So let's start. So the first thing we should know about what is chemical potential is and what is its significance. Actually, this chemical potential term was first introduced by G.N. Lewis. Okay, and what is this chemical potential is? Chemical potential is nothing but molar or partial molar Gibbs free energy, and it is represented by mu, right? And this mu star is used for pure substance. G is the Gibbs free energy, N is the number of moles, so G by N is the molar Gibbs free energy. Now one question will arise here, that to represent chemical potential, why we are using Gibbs free energy? Okay, actually the reason is G is the most important in explaining spontaneity of a reaction. Spontaneity of a reaction. From classical thermodynamics point of view, we know that if del G at constant temperature and pressure is less than 0, then the reaction is spontaneous. And if del G at constant temperature and pressure is greater than 0, then the reaction is non-spontaneous. Here comes the important thing, that at constant temperature and pressure. Because most of the chemical reaction will occur at constant temperature and pressure. And therefore, it is easier to represent chemical potential in the form of molar or partial molar Gibbs free energy. Now I am coming to the concept of partial molar Gibbs free energy. Okay. Suppose in case of solution means more than one component is there. This is for a particular one component. This equation, the first equation, is for a one component. In case of solution, plenty of components are there. When we are representing only one component among the other component, from the presence of other components, like here, like N1, N2, N3, Ni, different components are present, but we are only interested to represent chemical potential of the ith component in the solution. Then we will use this equation. And here the temperature and pressure should be constant, and the other number of moles of the other components should be constant, right? Like in this case, Nj is one component, Ni is other component. So when we are measuring the chemical potential of ith component, then the number of moles of jth component should be constant and this should not be equal. Okay, so this is the concept of partial molar Gibbs free energy when to represent chemical potential of a solution. Okay. Now we know that chemical potential is a measure of escaping tendency, right? So I will explain here why it is a measure of, why it is called the measure of escaping tendency. Okay. This is an isolated system. Here subsystem A and B are separated by a diathermal non-rigid boundary. This is diathermal non-rigid boundary. Okay. Now suppose dn number of moles is transferred from subsystem A to B. Okay. So if we want to see the change of free energy of individual systems, like for A, dg equal to mu A star dna, right? Why? Because we know that dg dna at constant at p. From there we can develop this one. Now for dgb, change in free energy for subsystem B, we can write that star dnv. Since dn number of moles is transferred from A to B, so definitely dn amount is reduced in A, and same number of moles is added to B. Therefore we can write that mu A star equal to minus dn and mu B star equal to plus dn. If we want to see the total change of free energy of the whole system, so we have to add these two terms. Now from this, by adding these two terms, the final equation will be this. This is the final equation, right? This is the final equation. Now from this equation we can draw three conclusions. Conclusion number one: if mu A star is greater than mu B star, then dg is less than 0. So obviously if the A has higher chemical potential than B, then matter from A to B will transfer spontaneously. Equation number 2, so conclusion number 2, if mu A star equal to mu B star, then dg is 0. That means the two systems will be in the equilibrium state. If mu B star is greater than mu A star, then dg is greater than 0. That means the transfer will be non-spontaneous. That is, the opposite process will be non-spontaneous. So among these three conclusions, the most important conclusion is the first one, to explain the escaping tendency. That means why it is called the escaping tendency, because if a system has higher chemical potential, then it can easily spontaneously transfer from to the lower chemical potential. And it is true for the other potentials. Suppose in case of electrical, if there is some electrical gradient, okay, or you can say that gradient of electric potential, then charge from high potential to low potential. Similarly, if there is a gradient of temperature, so heat can transfer from higher temperature to lower temperature. Same thing happen in case of gradient of pressure. Then also a frictionless boundary can move from higher pressure to lower pressure. Okay. And in the same way, if there is a potential gradient, so if there is a potential gradient, amount can transfer from higher potential to lower potential. And that is why this chemical potential is told the measure of escaping tendency. So today we'll stop our discussion here. We'll continue our discussion from here in the next video. So thank you very much. Please share your comments and subscribe our channel to see more videos related to physical chemistry or organic chemistry. Thank you very much.